Hi, welcome back. Today we're going to continue talking about quotient vector spaces. And the picture to keep in mind is the one that we ended on last time, where if you take just a subspace, so that's like that plane S through the origin, then if you shift that subspace, so if you look at a bunch of slices of R3, you can break R3 up into all these planes, and then each plane looks like some vector plus every vector in S, right? So that's why this blue plane is labeled V plus S, because you can think of it as the vector V that's on the plane plus every vector in S, right? So it's like you're going entirely in this direction. And what we said we would do is we would form a vector space, a new vector space, where the vectors were actually the planes through the origin, right? So each plane is a vector. And if you have two different planes, how do you add them together? You just take any vector on the first plane plus any vector on the second plane. That'll give you some new vector. That will define a different plane that's parallel, right? And it doesn't matter which vectors you pick on the first plane and the second plane, you'll always end up on the same third plane. So that's the idea of a quotient space. And if we think about this picture, you can sort of just say that each plane is just determined by its height, right, on the z-axis. So if you think of a quotient space here where every vector is one of the planes, the quotient space should behave just like R, right? It should behave just like the heights tell you exactly what the vector is. So that's the thing to have in mind. But let's now make the definition. Okay, so here's the definition. So let S be a subspace of V, any subspace you want. Okay, then the quotient space V mod S, that is how you read it. V mod S is the set of all affine subspaces of V which are parallel to S. Right, that is, remember the affine subspaces parallel to V, to S, were just some vector plus S, right? So V mod S, its vectors look like a vector V plus all of S, where V is in V. Again, don't forget the picture. Don't forget the picture. The picture is that this is S, some plane, some subspace. And the set of vectors look like, if this is V, V plus S is this plane. This will be one of the vectors in my quotient space. Of course, there's more than one way to write V plus S, right? Because this blue plane is both this vector plus every vector in S, but it's also this vector, V prime, plus every vector in S. Right? So this is the same thing as V prime plus S. Just like when you look at the integers mod 5, the equivalence class of 1 is the same thing as the equivalence class of 6. There's different ways to write it, but they both consist of all of the integers 1, 6, 11, 16, -4, -9, etc. Okay, so another way to write this is the set of all equivalence classes of V, where V is in V. Okay, so here the equivalence class of V means all of the entire plane, the entire affine space parallel to S containing V. Right, so this is like the equivalence class of V. And in the picture, it's the plane containing V. In general, it will be the affine subspace containing V that's parallel to S. Okay, so once you make this definition, I'm calling it a space, which must mean that it has to be a vector space, which means that we need some notion of adding vectors and scalar multiplying vectors. In other words, in this picture, I need some notion of adding planes and scalar multiplying planes. And that's exactly what the next theorem says. Here's the theorem. V mod S is a vector space where if you look at what the addition and the scalar multiplication should be, so if I need to take a vector inside of V mod S, so every vector is a plane that looks like this. You could also write this as the equivalence class of V. Maybe I should take two vectors, actually. W plus S. Right, so you can think of this as W. And C is a scalar. We define V plus S plus W plus S to be equal to V plus W plus S. Right, like this. And C times V plus S to be equal to CV plus S. Okay, so again, each time I have a vector plus S, I mean an entire equivalence class of vectors. I mean, take that entire plane, right? So here I'm saying take the entire plane containing V and the entire plane containing W. What its sum will be, it needs to be another vector, it needs to be another plane. What I'm saying is take the plane containing V plus W. Right, so all three of these things are planes. So naturally what we need to show is we need to show that if you take any vector from this plane and any vector from this plane, you'll get a vector in this plane. Otherwise, it doesn't make sense to add the planes, right? Similarly, this is saying if I want to scalar multiply this plane, the plane containing V plus S, I'll get a new plane. It's the plane containing CV. Okay. So here's one thing we need to show. So we need to show that these operations are well defined. Right? Again, I'm trying to add two planes. That means that this plane contains infinitely many vectors. In other words, there's infinitely many different ways to write that plane. There's also infinitely many different ways to write this plane, and there's infinitely many ways to write this plane. But when I write it as V plus S, I'm choosing one way to write it. And when I write it as W plus S, I'm choosing one way to write it. And I'm defining this sum in terms of that V and that W. But what if I had chosen a different vector on the plane and a different vector on the plane? My sum would be different, but you'll get the same plane, which is what we need to check. It's just the same thing as when you say there's a well-defined addition in Z mod 5, like this. When you say this, what you're saying is it doesn't matter which element in the equivalence class of 1 you take. If you took 11 here, and instead of 3 you took -2, that's two different ways to write these equivalence classes. You get 9, but that is the equivalence class of 4. So in other words, it doesn't matter which representative you chose of each equivalence class. We need to show that for this definition. Okay, so suppose that V plus S equals V prime plus S. In other words, I have two vectors on the same plane, or that define the same plane, and W plus S equals W prime plus S. Right, so these two planes are the same, I've just written them differently, and these two planes are the same, I've just written them differently. Okay, well, we need to show that if you choose to add like this, that this is actually equal to V prime plus S plus W prime plus S. This is a different way to add the same two planes. Okay, now by definition, this is the plane containing V plus W. And by definition, this is the plane containing V prime plus W prime. Okay, how can I tell whether or not these are the same plane? Well, this goes back to the lemma that we saw last time. It's right here. The lemma says that two planes are the same if and only if their difference lies in S. W plus S is the same plane as V plus S, if and only if W minus V is in S. Okay, I didn't prove it, but the proof is in the notes. And it's the kind of proof that you need to look at yourself. So we know. So what I'm trying to say is this is the one that we need to show, right? I don't know this equality yet. That's the one I need to show. What I do know is that the two equalities I do have, because that's a definition of addition. Okay, well, we know that these two things will be the same plane. This plane equals this plane if and only if the difference is in S. That's by the lemma. Right? Again, I'm going to keep on making points like this as we go. This is a plane. This is a plane. So to say that they're equal means that they're the same plane, right? On the other hand, this is a vector and this is a vector. So I know how to add vectors. Those are just regular old vectors. I'm just checking if this difference is in the subspace. Well, what is this difference? This difference is v minus v prime plus w minus w prime. Okay, but now since I'm assuming that v plus s equals v prime plus s, that means that this vector is in S. And I'm assuming that w plus s equals w prime plus s, that means that this vector is also in S. Sorry, there's a right. This is right. And now S is a subspace. So it's closed under addition, so this vector is in S. Right, this shows that the definition only works because S is a subspace. If you take something that's not a subspace, like a plane that's not through the origin, you won't be able to do this process. You won't be able to add planes. Okay? Now, what about scalar multiplication? Right, so now suppose that v plus s equals v prime plus s. Again, so suppose I have two different vectors that are giving me the same plane. Let r be a real number. Then I want to understand, well, if I scalar multiply this plane, does it equal, sorry, I chose C. Does it equal this plane? Okay, but the definition of scalar multiplication that we gave is that this is the plane containing CV, and that one is the plane containing CV prime. How do I know whether this is the same plane? So these are the same. So if and only if the difference is in S. Right, but of course this difference is just C times V minus V prime. And again, since I'm assuming V plus S is equal to V prime plus S, that means that this thing is in S. And since S is a subspace, it's closed under scalar multiplication, so this whole vector is in S. And that shows that my definition of scalar multiplication doesn't depend on which representative I chose for the plane, which vector I chose on the plane. Okay. Now, I think that it's better to use the notation v plus s and w plus s to remind yourself of the difference between a vector in V and an entire plane containing that vector. But another way to rewrite, and also it's sort of clear where the addition is happening, but another way to write this theorem is just to say that if you take the equivalence class of V and W in V, then if you take the equivalence class of V plus the equivalence class of W, you get the equivalence class of V plus W. And if you let R be a real number, or C be a real number rather, you take the scalar multiply of this new vector, which is a whole plane, it's the same thing as the plane containing the scalar multiple of V. Okay, so this is thinking of it in terms of equivalence classes, right? So this is the equivalence class of V. Okay, and notice that this is one of the notations for the integers mod n, where you put brackets around there, right? So again, in Z mod 5, if you take, right, A and B in Z mod 5, that's like taking an entire equivalence class of integers. Then you define addition between these equivalence classes to be the equivalence class of the integer A plus B. So it's, by total analogy, this is what's happening for quotient spaces as well. Okay, and for that reason, actually, if V equals W, we sometimes write V is equivalent to W mod this plane S. So this is basically borrowing from the modular arithmetic notation. Okay, now before we go on to the thing that I said we would, which was understanding the polynomial, the roots and this of a companion, the roots of a polynomial and the eigenvalues of the companion matrix, we need to make note of a couple of more facts. So if S is a subspace of V and I take the quotient space, there exists a linear transformation V to V mod S called the quotient map, usually denoted pi, that sends the vector V to the plane containing V. It's the most natural map you could hope for. Okay, and of course there's going to be a function like this, right? You just send V to the plane containing V. That's a reasonable function. The content of this definition really is that that happens to be a linear transformation. In other words, it plays nice with addition and scalar multiplication, which allows us to understand the following thing, which is what is the dimension of V mod S? This is the dimension of V minus the dimension of S. Okay, think about that in terms of this picture. Here the vector space V is R3, and the subspace S is two-dimensional. So if you mod out by a two-dimensional thing, what we're doing is we're breaking up R3 into a bunch of planes parallel to the origin, parallel to S. And so what you're getting is a one-dimensional space because they're all parameterized by their height above the xy plane. On the other hand, if you took, say, S to be just a line through the origin, now if you look at all the parallel lines, you've got a bunch of lines that are parallel in this direction, right? So, and then, but you could also push them in and out of the page. So, like, this is a whole bunch of parallel subspaces, right? But also you can get some more parallel subspaces coming out of the page. So you'll have a two-dimensional space of subspaces, right? S is a line. You look at all the lines parallel to S, that sweeps out in one direction. And then you can also have all lines parallel to S in this direction. It sweeps out in two directions, and then it'll fill up the entire space, right? Like a bunch of straws covering, like a bunch of straws inside of a cube, right? You have a two-dimensional space of straws. Okay, and this just follows from the rank nullity theorem. Why does this follow from the rank nullity theorem? Well, what does the rank nullity theorem say? So consider the map, the quotient map, pi from V to V mod S. Right, what the rank nullity theorem says is that the dimension of the range of pi plus the dimension of the kernel of pi is equal to the dimension of V. This is one statement of the rank nullity theorem in terms of the range and kernel of linear maps. Okay, well, what is the range of pi? The range of pi is all of the vectors that pi actually hits. But of course, we're defining pi by setting v to v plus s, which means that we're going to hit every single plane parallel to s, because we're allowing any vector v to be plugged into pi, so we'll get any plane we want. So this range of pi is just v mod s. So then it just becomes an issue of what is the kernel, right? So dimension of v mod s will equal to the dimension of v minus the dimension of the kernel of pi. And so we need to understand what is the kernel of pi. If the kernel of pi is s, then we're done. That should be our guess, right? Because, so is this s? Well, to understand that, we need to understand what does it mean to be in the kernel of pi. To be in the kernel of pi means that you get mapped over to the zero vector, right? So the kernel of pi is equal to the set of all vectors v and v, such that pi of v is equal to the zero vector. Well, what is the zero vector of v mod s? It's the plane 0 plus s. In other words, it's just s. Right? It's the plane parallel to s containing the zero vector. It's just s. Now, which vectors in v map over to 0 plus s, right? So which v in v satisfy pi of v equals 0 plus s? Well, this is exactly the plane v plus s. So what does it mean to say that v plus s equals 0 plus s? It means exactly that v minus 0 is in s. So this is exactly the v in v such that v minus 0 is in s. In other words, it's all the ones where v itself is in s. So the kernel of pi is exactly s, which tells us what we want. The dimension of v mod s is the dimension of v minus the dimension of s. Okay, now that maybe we have a slightly better idea of what quotient spaces will be, I want to go back to the idea of polynomials, where actually the story is a little bit more complicated. Because here's the thing to notice. For these quotient vector spaces, there's only a vector space structure. In other words, these planes, I can add them and I can scalar multiply them. But if you consider Z5, there's more structure. You can multiply equivalence classes as well. And it doesn't make sense to say that you can multiply vectors generally. But you can multiply polynomials, which means when you think of the polynomials as a vector space, there's an extra structure. So it turns out that if I consider quotient spaces of the polynomial vector space, it will actually be a little bit more similar to Z mod 5. Okay, so let's go back to polynomials in one variable over R. Okay, so what we're going to do is we're going to see that this is going to be very much like the integers, and we're going to take a quotient of R adjoint x. We're going to take a thing that looks like this. We're going to quotient out by a polynomial. I haven't introduced any of this notation yet, so don't worry about it. But this thing will be just like Z mod 5. Again, the difference being, in a general vector space, you can just add and scalar multiply. But if you're dealing with polynomials, you know how to multiply two polynomials together. In other words, there's a notion of multiplication amongst your vectors, which normally isn't there. Same thing is true for the integers mod 5. You can add, or the integers indeed, you can add integers and you can multiply integers. Okay, so we're going to define, we'll see we will define this quotient vector space. Okay, so and it will be enough to just fix some polynomial. It turns out that you can do this with any polynomial you want, but let's fix our favorite polynomial, x to the fifth minus 20x to the fourth plus 8x squared minus 10. Okay, so now what I'm going to do is I'm going to define a bunch of equivalence classes of polynomials inside of R adjoin x using this polynomial p. Okay, so this polynomial will be like the number 5. When you talk about z mod 5, you pick a number and you create a quotient space from the integers. You look at a bunch of equivalence classes of integers with respect to this number 5. We're now going to look at equivalence classes of polynomials with respect to this polynomial p. Okay, so we create equivalence classes of polynomials. They'll look like this. You take any polynomial and you look at its equivalence class, and this will consist of all polynomials b such that ax minus bx is a multiple of p of x. Okay, so our equivalence class will be, you pick a representative a, and you look at all of the polynomials that are a multiple of p of x away from a. Okay, in other words, this is saying, maybe I should take by analogy, you take the equivalence class of an integer m modulo 5, you look at all of the integers n such that m minus n is a multiple of 5. This is exactly what you do for the integers mod 5. We're going to do this with polynomials. Now, how do you figure out which polynomials are the same, give you the same equivalence class? You can just divide m by 5 and divide n by 5 and see if they have the same remainder. Right? So if you take m equals 5q plus r and n equals 5q prime plus r prime, if these remainders are the same, then m and n, so if r equals r prime, then m and n will give you the same equivalence class. And the thing about polynomials is we also have an algorithm for dividing polynomials. So what will turn out that if you could divide a by p with some remainder polynomial, and you divide b by p with some other remainder polynomial, then if these two polynomials are the same, then the equivalence class of a is equal to the equivalence class of b. And this is just the normal polynomial long division that you learned a long time ago. Okay, so let me just show you what I mean. Let's take a of x to be the polynomial x to the 6th plus 1. Okay, well, I want to know the remainder after you divide by p. Well, how do you do that? So you write x to the 6th plus 0x to the 5th plus 0x to the 4th plus 0x cubed plus 0x squared plus 0x plus 1. And you divide that by x to the 5th minus 20x to the 4th plus 8x squared minus 10. And you can do the long division. So you get an x here, you get x to the 6th minus 20x to the 5th plus 8x cubed minus 10x. And then you subtract, you get 20x to the 5th minus 8x cubed, right, plus 10x. So then you get a plus 20 term, you get 20x to the 5th minus 400 x to the fourth plus 160 x squared minus 200. You subtract again, and the remainder you get is 400x to the fourth minus 160x squared. Oh, I'm missing a minus 8x cubed. Minus 8x cubed minus 160x squared plus 10x plus 200 and 1. I forgot to bring down my plus 1 here. So this polynomial, if you divide it by p, you get that x to the 6 plus 1 is equal to x plus 20 times p plus this polynomial. Right, this thing is the remainder. And so in the quotient space, you have that x to the 6 plus 1 is congruent to r of x modulo p. Okay, and so just like for integers mod 5, the most natural choices of representatives for each equivalence class were the remainders when you divide it by 5 as much as possible, right? We'll do the same thing in this quotient space. So just like in Z5, in Rx mod Px, we choose, or we can choose, a nice set of representatives. Right? The remainders after division. After long division. Okay. Of course, when you divide an integer by 5, it's very easy to see what the remainders are. Right? The remainders are 0, 1, 2, 3, 4. But when I'm dividing by this insane polynomial p of x, I'm getting insane remainders. I got a remainder of 400x to the fourth minus 8x cubed minus 160x squared plus 10x plus 201. So, I mean, I'll get infinitely many remainders. Right? The point is that any polynomial of degree less than or equal to 4 is definitely already a remainder. Because if you try to divide it by p, you're just going to get 0 plus that polynomial. It's just like you can't divide 5 by any number less than 5. So note that any polynomial of degree less than or equal to 4 is going to be a remainder. Right? In other words, everything in this this vector space. Okay, but now if I have a polynomial of degree greater than or equal to 5, then I should be able to divide by p and get a polynomial remainder of less than or equal to 4. Just like, again, if you take the number 5, you divide it by any number bigger than or equal to 5, you can get a remainder between 0 and 4. And so any polynomial a with degree of a greater than or equal to 5, we can long divide to write a of x equals p of x times q of x plus r of x, where the degree of r of x is less than or equal to 4. In other words, everything in this vector space will be a remainder, and also you can always get a remainder in that vector space. In other words, the space of remainders is exactly r of x less than or equal to 4. Is the possible remainders. are exactly this vector space, which means there's a 5-dimensional space of remainders. The space of remainders is a vector space of dimension 5. Right, so there is a bijection between the equivalence classes of polynomials in this quotient space and this set of possible remainders. Again, the thing to think is there's a bijection between the equivalence classes of integers in Z mod 5 and the set 0, 1, 2, 3, 4. Exactly the same thing. These are all the possible remainders you can get. All the possible remainders you can get when you divide by the polynomial p of x is just every polynomial less than or equal to 4. Okay, and so remember, on this side, the numbers are equivalence classes. Of course, the remainders are just integers. Right, so up here, the remainders are going to look like just polynomials. But inside of the quotient space, it will be the equivalence class of the remainders. This is all the polynomials that have that remainder when you divide by p. Okay, so it turns out that in this vector space, we have the following theorem or proposition. Okay, so 1, the elements or the vectors of the quotient space are equivalence classes of polynomials modulo p of x. Right, each equivalence class is represented by a remainder in R adjoint x after dividing by p adjoint x. Sorry, by p of x. Again, the thing to keep in mind is imagine the integers. The integers mod 5 is a collection of equivalence classes of integers, and each equivalence class is represented by a unique remainder after you divide by 5. Same thing here for R adjoint x mod p of x. I forgot some parentheses there. 2, this thing is a vector space via, how do you add two equivalence classes? You just take the equivalence class of the sum of those polynomials, and if you scalar multiply an equivalence class, you just get the equivalence class of the scalar multiple. Okay, here's an important thing. How big should we expect this space to be? Well, Z mod 5 had size 5. There's a bijection between this quotient space and the space of polynomials of degree less than or equal to 4, which is a 5-dimensional vector space. So a basis is given by the following: 1x x squared up to x to the d minus 1. So let's suppose that p has degree d. Okay, in other words, if I look inside of the quotient space, every vector will be a linear combination of one of these d polynomials. Okay, which means that the dimension of this vector space is equal to d, the degree of p. Again, by analogy, the size of Z mod 5 is 5. which is the size of 5. Okay. Now I want to understand, I want to use this understanding to understand the companion matrix. So here's the proof that the companion matrix has eigenvalues, which are the roots of P. Okay, and since this is already complicated enough, we're again just going to consider the case when P of x is our favorite polynomial, this one. Okay, but the general idea will be contained in the proof. Okay, and here's the trick. Consider the linear transformation. I'm going to call it T, and it's going to go from this quotient vector space to itself. What does it do? So it takes a polynomial, and remember the polynomials here are going to be equivalence classes of polynomials. So it'll take a vector r adjoint x, r of x, to the vector x times r of x. So it multiplies the polynomial by x and takes the equivalence class. Okay, that is a good example. If you just take, the equivalence class of 2x squared plus 1, that's a perfectly good remainder when you divide by p of x. You get 2x cubed plus x. That equivalence class of polynomials. Okay, but if you take a polynomial with a higher degree, so if you take, say, x to the 4th plus 1, then you'll get x to the 5th plus 1, but this remainder is too big, right? The remainder should have degree less than or equal to 4. So this is equal to a smaller, this has a representative that's a smaller degree. And the point is that x to the 5th plus 1 is equal to p of x plus 20x to the 4th minus 8x squared plus 10 plus 1. Right, that's exactly what x to the 5th plus 1 is. If you look at p of x and you add that thing, then you'll get x to the 5th plus 1. And now, this is a multiple of p of x, and this is a remainder, so this is equal to 20x to the 4th minus 8x squared plus 10 plus 1, which is plus 11. Okay, so of course you can still write the equivalence class like this, but we said the most natural thing to do is to choose a set of representatives for your equivalence classes that are all small degree. Okay, and it turns out that this is a linear transformation. I'm not going to check it. You can check it. And now the question becomes, what is the matrix of this linear transformation? What is the matrix of T? How do you find the matrix of linear transformation? You compute what it does to a basis. What is a basis? Well, a basis of this quotient space is given by 1, x, x squared, x cubed, x to the 4th. Now, what does T do to these things? T sends 1 to x, sends x to x squared, sends x squared to x cubed, sends x cubed to x to the 4th, and it sends x to the 4th to x to the 5th. But I need to know how to write x to the 5th in terms of this basis. But x to the 5th is just, I need my polynomial p again, 20x to the 4th minus 8x squared plus 10. Because that's the remainder when you divide x to the 5th by p of x. Right. So that means that x to the 5th is 20x to the 4th minus 8x squared plus 10 times 1 in terms of our basis. So what's the matrix? the matrix for T, the first column is what happens when you plug in the first basis vector. What do you get? You get x, which is 0 times 1 plus x plus 0 times x squared plus 0 times x cubed plus 0 times x to the fourth. In other words, with respect to this basis, the first column is this column. Similarly, what happens to the second basis vector? The second basis vector goes to the third basis vector. So it goes here. The third basis vector goes to the fourth basis vector. The fourth basis vector goes to the fifth basis vector. What happens to the fifth basis vector? It goes to 10 times the first minus 8 times the third plus 20 times the fifth. Right? So it goes to 10, 0, negative 8, 0, 20. In other words, the linear transformation T, its matrix is exactly the companion matrix of P. This is really where the companion matrix comes from, believe it or not. If you take modern algebra at the graduate level, you'll see that the way that you think about these companion matrices is exactly the matrix representing the linear transformation multiplication by x inside of the quotient space R adjoint x mod P of x. And that's the reason that this companion matrix has such a nice property. Okay, so now we just need to understand, so this is the matrix of T. Let me just understand what are the eigenvalues of T, because then those will be the eigenvalues of AP. So what are the eigenvalues of T? Okay, so suppose that R adjoint x is an eigenvector, with eigenvalue lambda. Right? That means that T of the equivalence class of R is equal to lambda times the equivalence class of R. What does that say? Well, T of R was supposed to just be multiplying by x. Right? Let me make sure that this looks like an x and not like a lambda. In other words, since this equivalence class equals this equivalence class, that means that x Rx minus lambda Rx, that these two things are the same equivalence class. In other words, these two things differ by a multiple of P. These two polynomials are a multiple of P away from each other. Just like if you say two equivalence classes mod 5 are the same, the difference is a multiple of 5. Okay, so if you have an eigenvector with eigenvalue lambda, it means exactly that x Rx minus lambda Rx is a multiple of P of x. And this is just, these are polynomials, these are not equivalence classes at this point. Now, look at the left-hand side and look at the right-hand side. Okay, this side has degree less than or equal to 5, because all of our remainders are degree less than or equal to 4, and then I had multiplied it by x, and so I get degree less than or equal to 5. This thing has degree 5, which means that this polynomial must have degree 0. This must be a constant. So this side is also x minus lambda times R of x, which tells you exactly that P of x has a factor of x minus lambda. So x minus lambda divides p of x. In other words, every eigenvalue of a is a root of p. But now there are 5 eigenvalues of a, and p has 5 roots, and so the eigenvalues of a must be exactly the roots of p. And this is the reason why, this is the real reason why the companion matrix has the same eigenvalues as the roots of the polynomial. Because it's really the matrix of a really nice transformation from the quotient space to itself. Okay. Now this diversion on quotient spaces, I think, is really quite hard. It's really hard to understand quotient spaces, especially just in the span of a couple lectures. But the more times you see it, the more comfortable you become with it, which is why I wanted to introduce it now. If you take 412 or 402 in the future, you'll see quotient spaces again, and you'll have more experience to draw upon as you think about it. Even if you aren't a math major, at some point you may see quotient spaces again, even in computer science, and the more times you see it, the better. Okay, so if you're confused a little bit, that's okay. That's normal. There won't be many, if any, homework problems that really use a lot of deep things about quotient vector spaces. You should definitely know the definition, and you should definitely at least understand pictures like this. Yeah, but next lecture we'll go back to more concrete things than these quotient vector spaces, and we'll start talking about singular value decomposition, which will take us several lectures to cover, including a bunch of cool applications. All right, see you then.